Hello, so I'm back again in this 10 lecture series. So today I'm going to talk on a new topic on quantum theory of graphene. So let me get started. Like I said, so it is about quantum theory of graphene. So before we get started, let's see why graphene is so exciting and what is the so much noise about graphene. Because graphene has so many exotic behaviors that hasn't been seen in any other materials. For example, uh, like quantum Mole effect at even at room temperature. So typically it requires much lower temperatures and high magnetic the materials. Also, this is slightly different from quantum Hall effect seen in two-dimensional gas systems. Also, Barry phase, uh, this is about the curvature related property. So then this ballistic transport in graphene also it supports the Klein paradox. So then also there are so many other exotic behaviors that makes graphene very exciting material for many researchers. So in terms of quantum theory of graphene, actually, if you look at graphene's electronic structure, actually quantum point electron structure of other metals and semiconductors in other materials. So also this supports emergent relativistic quantum mechanics. Uh, uh, Mostly we are talking about the Dirac equation. So compared to most of other semiconductors, we use the conventional Schrodinger equation even to study the quantum properties. Here we are talking about relativistic quantum mechanics. So also graphene and this relativistic quantum mechanics can go both ways. For example, uh, so insights about graphene can be gained from relativistic quantum mechanics, and also insights about uh, relativistic quantum mechanics can be gained from graphene properties of graphene. So it can go either way. So and also, like I said, this quantum Mole effect in graphene that is very exciting. So it's a little bit different from conventional quantum Mole effect because we have this something called the pseudo spin properties come into play. So in terms of properties of graphene, so this is just one atom thick layer, right? So because you have this single carbon atom arranged in honeycomb structure in two-dimensional lattice. So that also they have the zero band gaps. So because at these Dirac points, the conduction and valence band, they just touch at a single point, so giving your band mass 0. So this makes it massless Dirac fermion. So also because of this single atom thick uh, layer of carbon, so it is highly transparent and also highly flexible. So then the resistivity of graphene is very low. Resistivity is very low. That means your conductivity is extremely high, uh, even greater than silver. The resistivity of graphene is smaller than resistivity of silver. So one of the best conducting metals. So also the mobility of graphene, the electron mobility of graphene can be as high as 300,000 centimeters squared per volts per second, depending on how you prepare this graphene material. So in addition to this, there are so many other exciting properties of graphene. So before we get started, since graphene is made out of carbon, so we should look at carbon in general. So how this carbon uh, in carbon atoms, how the electrons are arranged and how they are going to be hybridized and make these different structures. We know carbon is unique because it can make crystals of different form. We know one thing is graphite, that graphene, the stacked layers of graphene. Then also we know another structure, diamonds. They are completely different properties they have. So that means even though they are all carbon materials, so the way they are hybridized, so makes them different in crystal structure and also result in properties. So that's why it's important to understand how these electrons are arranged in these carbon materials, because we know in carbon in ground state, so they have these 6 electrons, 2 electrons in the core state, like 1s2, then you have 4 electrons in the valence state, so that means you have 2 in the 2s band and 2 in 2p band. So we have px and py electrons in the this 2p level. So but since carbon has the ability to hybridize, so this if you look at the valence band, like 2s electrons and 2p electrons. In the 2s you have spin up and spin down electrons. So in the 2p you have both spin up state. So now in the excited state, one of these electrons from the 2s can be exchanged to 2p state. So leaving only 1 electron in the 2s state and 3 electrons in 2p states. Now this S and P, these 2s and 2p, they can hybridize. So in some cases, like here shown in this case, you can have all these 2p states. So that means that's what we have here, right? So only 1 electron is coming here. That means you have 1 s electron and 1 2p electron, that we call the sp2 hybridized state. So then you have since s and p 2 from p and 1 from s, so when they hybridize, you are left with 1 of the p electron. So we call the pc orbital. So that is unhybridized, right? So because other 2 from this p orbital, they are hybridized with s, so making it sp2. So then you have 1 unhybridized, we call the p orbital. That gives rise to the something called the pi bond. So this sp2 will give rise to sp2 bonding. If you look at here, so these are you have this sp2 bonds. So then you have pc orbital that is perpendicular to the plane of the this sp2 plane. So this is one way of hybridizing. So other ways you can have sp3 hybridized. So that way you have all these 3 and also pc1 also hybridized. So that way you don't have any unhybridized orbitals. That's why diamond, if you take, for example, diamond doesn't have any this p orbital, so that's why they are electrically insulating. But in the case of graphene, that is sp2 hybridized, so that means 1 from this s and 2 from p, so making it sp2, so then leaving 1 electron unhybridized, that's the p orbital. So because this sp2 is, if you look at many allotropes of carbon, so starting from Buckminster-Fullerene C60 molecules, so then we have carbon nanotubes, then we have this graphene. So these all have sp2 bonded this honeycomb structures, right? But when they fold, so sometimes you have to have this pentagon structures to make it cylindrical uninterrupted structure. But if you take diamond, so diamond is all sp3, so that's completely different structure. But C60 graphene and nanotubes, where some way has close structural similarities. So, but graphene is, you can see here, it's just single layer of graphite. So by stacking millions of these graphene layers, you get the graphite. So two of the materials, so single nanotubes and graphene. So you can think single or carbon nanotubes as roll in a single layer of graphene, right? So, but single wall nanotubes, they are considered to be 1D material because it has very long this aspect ratio. So compared to the diameter of the tube. So important thing about nanotube is they can come in these two flavors, metallic or semiconducting, depending how you roll this one. That's called the chirality of the that nanotubes. Then they also have pretty high mobility, even as high as 120,000. And also it has very high carrying capacity. So also extremely high mechanical strength. So graphene, on the other hand, so they are sp2 bonded carbon. So this completely 2D honeycomb crystal lattice. So like I said, carrier mobility can be really high, as high as 200 to 300,000. Then low electrical resistivity we talked about, less than silver. And they also have very good mechanical properties because they are all sp2 bonded in that plane. So sp2 bonded, they are strong bonds, right? So they make covalent bonds. So they are strongly strong. But if you look at in the vertical, perpendicular to the plane, these are PC orbitals, right? So these are pi bands. So then if you have two or more layers, so that those walls are, those layers are interconnected by these PC orbitals. So they make some kind of van der Waals interaction that makes those the attraction between these layers pretty weak compared to very strong sp2 bonded strong bonds on the two-dimensional lattice. So now, like I said before, so if you look at this electronic levels, so we have this 2 electrons in the 1s state, right? They are both filled. Then we have 4 electrons, 2 on the 2s2 and 2 on 2p2. So then the other states are empty. So, but what happens is when you have this hybridization, so you have this 1 electron coming from 2s to 2p, right? So that makes it only 3 electrons in the sp2 band giving sigma band. So then the one left one is it gives you the pi orbital. So then that makes the pi orbital. So these 3, making the sp2, that gives you the sigma band. So then we have something called the bonding and anti-bonding. So if you have, this is sigma bonding band here, so then you have the anti-bonding band here, we call sigma star. So this pi band is basically perpendicular to the, or normal to the, this sp2 bonded, the planar, sp2, the honeycomb, the plane. So this sigma and sigma star, so these are all in plane. So they are all in the plane. So coming from the sp2, so these are this sp2 bond. So this is your pi bond here. So this sigma bonds are exceptionally strong. So they make that your structure very rigid. That's why graphene has very strong structure. So, but pi electrons, so they basically they are more like your electron is delocalized, right? So that gives you the conduction. That's the reason, because of that unhybridized pi electron, you have good electrical conduction. So that's something you don't have for sp3 bonded, so because like diamond. So now if you look at this pi bond, so that's the one contribute to the conduction, right? So we are talking about this pi and pi star, right? So it's coming from this p bond. So if you look at all the atoms together, so they each one has this pi and pi star. So then if you, because like I said, this has this one electron, pi electron. So if they want to move, because these are unhybridized, so these are, we call the delocalized electron, they can actually go from one atom to another atom by something called hopping. So that's how the current is carried in graphene, by hopping. So we call this is the, later we'll talk about the tight binding model. This is basically standard textbook problem of tight binding model. So, but if you look at tight binding model, so typical graphene crystal structure shown here. So you can see this, this hexagon is not a unit cell, right? So your unit cell actually contains two atoms. So for that reason, we pick these two sublattices. One sublattice shown in this blue, and other sublattice shown by this red. If you take all these 6 atoms, they don't make a the Bravo unit cell, right? Because they are not the same if you look from surrounding points. So, but each sublattice makes it real lattice. So that's why when you talk about graphene, we are talking about two sublattice crystals. Now, if you want to talk about the electronic structure of graphene, first we need to compare this one with metals and other semiconductors. If you consider metals, we know in metals you have your bands are filled up to something called the Fermi energy, right? So everything below Fermi energy is filled, everything above Fermi energy is unfilled. So we call the occupied and unoccupied state. So always occupied electron from the occupied state can be excited to the unoccupied states. So then also they have finite density of states at Fermi energy. So your density of state is finite at the Fermi energy, you can see here. So now in semiconductor, on the other hand, the one band is completely filled. So then you have a gap. So then you have the next band. So that means you can excite electrons from the field, we call this a valence band, to the unfilled band, that's the conduction band. If you have enough energy to overcome that gap, that's the band gap. So that energy can come from heat or can come from photons and things like that. But the important thing is you don't have any finite density of state at the Fermi energy. So because density of state here is 0 inside, but on the conduction band or valence band, you have finite density of states. So graphene, on the other hand, there's no gap. So between the field and unfilled states. So we call this is still your density of state at Fermi energy is 0. Also, there's no band gap, so 0 band gap. But ideally, your graphene density of state is more like this one. It's not like a typical band like in semiconductors. So they show this kind of behavior at near band the Fermi energy. They show very linear density of state with respect to your energy. So here you show the fields band and the empty band. So this is your Fermi energy. So also another important thing to understand is in standard semiconductor, we have parabolic band, right? So given by this p squared. over 2m. So here you have the conduction band and the valence band. So each band, if you measure from the top of your valence band, you can, here you measure from your, depending on which position you are measuring, you can write equation for your conduction band and the valence band. Here actually conduction band with respect to your conduction band minimum. So here with respect to valence band maximum. So but in graphene, so this they are no longer parabolic. You can see these are more like conical bands. So then also at this the Fermi energy position or zero energy position, they overlap. So we call this the Dirac point. So then your energy is no longer parabolic, it's linear, right? You can write related to your momentum, or your this is directly connected to your the wave vector k. So this actually that slope is the Fermi velocity. For graphene, this velocity is extremely high. It can be as high as 10 to the power 6 meters per second. So that's what making graphene very exciting. So then, since we are talking about this theory of relativity, we can connect this one to Einstein's theory for relativity. If you consider a stationary particle without moving, your momentum is 0, then the rest energy is given by E equals mc squared. But if you have momentum p, so we know E is given by this equation, E squared equals m squared c4 plus E squared p squared. If you take square root of that, E is given by this equation. So now if you like, we remember if we have a linear relationship, we show velocity given by dE by dP, right? So that's, if you differentiate this one, you get this equation. So just simply take the derivative of this equation with respect to P. So now if I plot this V as a function of P, so it shows this kind of behavior. For large P, this reaches velocity of light, but smaller P, so this region is very linear. So that slope is given by P over M. Right? That's more like a classical situation, right? When for low velocity, it gives the classical relationship P equals mv. So then if you have a massive particle like electron, so in this case, actually, since you don't have that curvature at the Dirac point, so we are basically talking about massless particle, right? Just like photon shown here in the bottom curve, because E is proportional to P. So since M equals 0, we know in this equation E C times P, but V is, in that case, for photon it is V equals C, right? So but relationship is very similar to what we had for graphene in the zero mass situation, but velocity for graphene is not exactly C, that is in something like 10 to the power 6 meters per second. But if you take something that has a mass, that's a massive particle, so then that has a mass, then if you use this equation, so in non-relativistic case for very small v, so we can write this one easily like p squared over 2m, so that gives you this parabolic behavior. So this is what you expect for standard semiconductors that has a mass like electron or any other electron hole or any other massive particle. But if you have a massless particle like graphene, that's similar to photon. We know in photon we have this linear energy momentum relationship. Now in terms of wave equation, so everybody remember energy operate is IH cross D over dt, momentum operate is minus IH cross grad. So if you assume plane wave, psi is Ci k dot r minus omega t. In the non-relativistic particles, so if you use Schrodinger equation with mass, if you have a mass, so then you can write E as p squared over 2m. So E is IH cross dc over dt. P squared becomes this h squared, grad squared, psi. So that is a Schrodinger equation. But in the relativistic case, this is for the non-relativistic case. In the relativistic case, we have something called the Klein-Gordon equation. For that, we need to start with this equation instead of this is the classical or non-relativistic equation. But in the relativistic case, this is your equation. Then again, if you use E as this IH cross over dt and P as minus IH cross grad, you get this. You just try. So this equation is called the Klein-Gordon equation. So this is actually something close to this Dirac equation what we use for graphene. So because in order to preserve particle conservation, this quantum theory requires a wave equation that is first order in time. Also in Dirac solution, so we talk about this sigma dot p approximation. So that is actually coming from looking at how to combine this term, this px squared plus py squared plus m squared, how you can connect this one with the this simple spin matrices. So this poly spin matrices. So that's basically question arise, how do you take the square root of this px squared plus py squared plus m squared without really taking the square root? So if you do some indirect methods, so if you take px squared plus this one, if I multiply or take the product with the unit matrix 1 0 0 1, I can write, if I do some manipulation, if you do this one, so actually this is you can write this one in terms of px with this Dirac or poly matrices, right? In terms of this one, then you can write this term as without any square root, like px times sigma x plus py times sigma y plus m times sigma c. So that's sigma x, sigma y, sigma c are given here. So then the Dirac equation you can write simply in this form. So that becomes your Dirac equation, right? So then starting from the this Klein-Gordon equation, you can arrive at the standard Dirac equation. So here psi is given by psi A and psi B. In graphene case, you can consider this A and B as coming from these two sublattices we were talking about. That's how people connect this Dirac equation with graphene situation. So yeah, that's how this low energy electronic structure of graphene. So you can describe this one as Dirac equation. So still your mass is 0. So the velocity in this case, c becomes actually Fermi velocity, right? So 10 to the power minus 10 to the power 6 meters per second. So that sublattices A and B, like here we have this blue and red sublattices, they can be this wave function in your Dirac equation. That's the emergence of this Dirac fermions in graphene. Then also the consequence of Dirac equation, we know Dirac equation has these two solutions, right? You have, when you take the square root, you have E as plus or minus. So this how we describe this particle antiparticle concept. So for example, if you have electron for negative, then you have proton, positron for positive. So that's always you have this particle antiparticle pair, right? That's a consequence of Dirac equation. Same thing in if you consider graphene as the Dirac particle, Dirac fermion, you have to have similar situation. We know that can be explained as if you consider this particle as your electron, then antiparticle is like hole in the semiconductor. So that's typical semiconductors. Also we have electron hole concept, but they have mass, right? But here also in graphene also we can consider, since we are using Dirac equation, you have to combine this antiparticle particle pair. So we combine that one as electron hole pair. So then another consequence of Dirac equation is, so since we know electrons have spins, right? So then we talked about the total angular momentum J given by sum of orbital angular momentum L and the spin angular momentum S. Then in the Z direction, if you have magnetic field, so say SC is given by plus minus H cross over 2. That is more like having up and down spin. So electrons we know have magnetic moment. So that's why we have the magnetism we talked before, right? So, but in graphene, so we talk about this this spin, but that we can combine these sublattices, right? If you when you consider the sublattice A and B, so that is you can think as actually having if you assign some spin so to this one sublattice and the other sublattice, so that is not the real spin that we usually talk about. We call those as pseudo spin, because we need to, since we are using the Dirac equation, we need to assign that spin concept, right? So but here we call that one, this psi A psi B, we assign something called pseudo spin. So we have that effect of pseudo spin come to play. Another important thing is, if you look at ordinary metals or semiconductors, when you have under magnetic field, they split into this something called Landau levels, right? So En is given by n plus half H cross. This EBOM means the cyclotron frequency omega c. So H cross c n plus half, n goes from 0 to, so that means n equals 0. You have this half H cross omega. So then you get different states. So depending on, they are equally spaced, right? So these are the Landau levels coming from for classical particles. But for the relativistic particles, that's going to be slightly different. Then when you have magnetic field, they split into energies that's given by square root of EH cross VF squared B times this N. N is this quantized levels. So in this case, you can see these numbers, they are no longer equally spaced because they are going like square root of N. So you can, when you go higher, they are getting closer and closer. So existence of Landau levels at 0 is deeply related to spin in Dirac equation. That's the important thing. That's all coming from this consequence of Dirac equation. So now I want to get to crystal structure of graphene. So if you look at, this is in the left, we have real space crystal. So you can see the two sublattices, one shown by this blue and other sublattice shown by yellow. So if you want to pick the primitive unit vectors, you can show it's coming from, if you take one of these yellow ones, so the one closest to the other two yellows, they are the two primitive vectors, A1 and A2. So then if you connect this one, that is the unit cell. So like that. So it's not like if you connect between two, they are not same, because every other point makes the real lattice points. So you can see my primitive real space unit vectors are A1 and A2. So how do you write this A1 and N2? I can write in terms of this my lattice constant A. If A is the distance between two atoms, I can easily write A1 and A2 as A1 is A over 2, this 3 square root of 3. That's very easy to find, right? If you calculate the distance y and distance x, you can easily find that is 3n square root of 3. Same way, a2, same x-axis, x coordinate will be negative minus 3. So this is a good exercise for you to do. Just calculate this coordinate starting from this. This is your 0 point. So you just calculate what is the x coordinate and y coordinate here, and x coordinate and y coordinate for here. These are my primitive vectors a1 and a2. Now, if I want to generate the reciprocal lattice vector that is in the reciprocal space kx and ky, so I need to calculate reciprocal space unit vectors. So we call b1 and b2. That we know it satisfies this equation. Ai bj is 2 pi times delta ij. That's the Kronecker delta. That means a1 b1 is 2 pi, a1 a2 b2 is 2 pi, but a1 b2 is 0, or a2 b1 is 0. If you use those equations with a1 a2, you can easily find your b1 is going to be 2 pi over 3a 1 square root of 3, b2 is 2 pi over 3a 1 minus square root of 3 in xy coordinates. So if you plot that one here, so these are my reciprocal lattice points here. So then my vectors b1 and b2 are given here. So I can easily write my these points, this in reciprocal lattice, we can find this k point, k prime. So this again, like this is k prime. So k prime. These points you can easily calculate if you know b1 and b2. So you can calculate these coordinates. It's basically if you take this one like 1/3 of this this length between b1 and b2, you can easily calculate k and k prime. Also, you can calculate the midpoint. We call the M point. That is, these are symmetry points in any brilliant. This is more like what we call the first brilliant zone, right? So that the reciprocal space. So that k and k prime you can easily calculate to be these numbers. These are simple geometry, right? So if you know b1 and b2, you can calculate k1 and k2, k and k prime. These are called the Dirac points. So if you look at this first brilliant zone, so that's what we have here. So the middle point we call is gamma. So then this point k prime, this middle point is called, if you make a perpendicular line, that we call the M point. So these are symmetry points in a crystal. So then another important thing to know is, if you take one point, what are the nearest neighbor distances? Suppose if I measure from this point, what is delta 1, what is delta 2, delta 3? You can easily calculate delta 1 to be this number. So delta, if you measure, this is my the origin. If this yellow dot is your origin, so the delta 3 would be minus 1 or minus a and 0. Then you can easily find what is delta 1 and delta 2, because we need this one when you want to calculate the nearest neighbor distance. So these are all simple geometries. So now I want to calculate the band structure of monolayer graphene. So we have to start with how to create my Hamiltonian, right? So to do this one, we can consider these two sublattices, one A sublattice and one B sublattice. A is all blue ones, B is all yellow ones. So then I can write my Hamiltonian as the binding approximation. Remember, we can have, so if you take each carbon atom, so we have these pi orbitals, right? We have bonding and antibonding pi orbitals. So these pi electrons are all delocalized electrons. So they are free to move. That's because unhybridized. So they can just hop between each atom. So we use that hopping integral or that parameter as t. Then I can write my Hamiltonian taking this creation operation for AI. A is all the vectors corresponding to the sublattice A with the subscript I. So B is all the positions related to sublattice B. So with the subscript J. So now if I write the total Hamiltonian, we need to take the sum of all I and J's, mostly for the nearest neighbors. So that you can write this Hamiltonian like that. So if you write this one, so you can keep writing, expand. This is only for the nearest neighbors. So this term I can, this is for any pair of these sublattice A positions and sublattice B. But if you only consider the ones closest to each atom, so then if I take one atom, so I can consider only the deltas, right? So you just add AI from the A sublattice. So then next one coming from B is only I plus delta, but that delta can be 1, 2, or 3. So then same, you have two terms like that. Then I have to do that one for all the I values, but in the A sublattice, right? Because yeah, first starting with that lattice, so then you have to consider for all the sublattice. You can easily separate that into two sums. So, but we know this the creation operator for A the sublattice A, I can write as square root of n by over 2. That because this is only from sublattice, right? So we have to half of the atoms. So that's why I have n over 2. That's the normalization constant. You have to write in terms of the position EIK in this plane wave form ik dot ri with the creation operator. So that is your creation operator AI plus. You can write in terms of sum of all k vectors for given ri position. So AI is the creation operator for position in the sublattice I position. So now if I want to combine this H, just substitute this A plus into this one. So then you have this you can substitute AI and BJ. So then you have other term, the Hermitian conjugate. So I didn't write that one. So you can easily write that part. So then if you take this one into this because also we know if you combine for this this relationship here, you can substitute this this part to be simply this one. So this coming from this one here. So if you go one step further, now you know the Hermitian conjugate is simply conjugate of this one, right? So that is your Hamiltonian. So we use this relationship here to get here. So now you can write this Hamiltonian as simply sum of, if I write some HK, the matrix element, so with some wave function H, but this psi wave function you can write as simply this AK, BK, right? So then psi star is this row vector AK plus BK. So then your HK is simply this one. So if you write this way, so your HK becomes minus T 0 delta K. So if you don't really understand this part, just start from here. HK is given by minus T. So that's all. We know this Hamiltonian. Then you can find the eigenvalue of this Hamiltonian, the matrix. So then you get the energy. So only thing we need to know what is this delta K. So delta K is nothing but this equation, right? So that nearest neighbor delta. So delta is basically these three values, right? Delta has a delta 1, delta 1, delta 3. You just add EIK. That's it. So if you know delta K, you know how to calculate delta K star. So then take the eigen value of that matrix, you get the energy. That's the band structure. Very simple. So then if you take the eigenvalue, this is what you get, right? So you know how to get the HK psi equals E psi. So if you take the matrix, so if you calculate, you get your, that is your energy. So this is the band structure. So only you are left with how to calculate delta K and delta K star. That's we know, right? That's very simple. This because we know delta, so then you can calculate delta K. So how do you do that? So if you take delta K, this one, so we know delta 1, delta 2, delta 3. Remember, I showed how to do that one. So now just calculate this term delta K, that is EIK delta 1. The delta goes from 1 to 3, right? So if you add these three, just simply add this one. If you do little bit algebra, you get this expression, that is delta K. Then delta K star is, you can take the conjugate of this one. Then just E plus or minus is scatter of T, that your delta K square, right? So delta K star, if you calculate, is your energy. That's your band structure energy. So this is function of Kx, Ky, Kc. So you can easily plot this one. So if you plot, this is what you see. So this is for the plus T, you get the top curve. For minus 1, you get this one. If you look at this one, you can see this has this 6 like hexagon, but it touches at these 6 points. These are the Dirac points. You can easily find those points where Ek becomes 0, right? If you solve this one equals 0, you can find Kx, Ky, and Kc. So actually it's Kx, Ky, right? So it's a two-dimensional curve. So this has Kx and Ky. So you can find these points. If you calculate that one, you will find these are exactly that Kx and Ky we found, the Dirac points. So they become 0 exactly at K and K prime. So this, if you plot, look at this at K and K prime, so they look like this one, right? So you have this one cone and another cone. We call this a K, or it can be K prime. So at that point, we usually define this one as electron and hole, or coming from bonding and antibonding bands. Here's another much more clear picture. You can see these are the valence band, conduction band. These are this K and K prime. K, K prime, K, K prime, K, K prime. At these points, this conduction and electron valence band, they touch each other as a cone. So at that point, you can see your curvature is infinity. So that means your band mass is 0. So at K and K prime, you have massless Dirac fermion. So then if you look at near this Dirac point, so this E is more linear, right? You can write E plus and minus as Fermi velocity times Q. Remember in Dirac equation, this E is going like C times your Q, but here it is VF times Q. It's still reminiscent of your Dirac equation. So if you go further up, you can see this is, if you look at in two-dimensional form, so gamma point, your K and K prime, this is the middle M point. I'm going from gamma to K and K prime, so this is in the middle. You just go this way. You can see at K point, this is actually your pi band, right? So this is pi and pi star. So they become linear energy relationship. So they are mostly coming from this. Then the red ones are sigma bands. So this coming from sp2, right? This blue curve, that is pi star band coming from that pc orbital perpendicular to the sp2 bands. So you can see at this range, these are pretty linear. So energy. So this is more like decoupling of your sp2 and pc, right? Because they are no longer together. So we decouple p band from the sp2 band. Three-dimensional way, you can think this one as, so this thing is I plot as three-dimensional case. You can see gamma point. So then you have M point and K point. Near K point, you have this Dirac cone. So then if you want to calculate the density of state of graphene, you can easily find density of state given by this equation, sum of all these delta functions. If you make this sum as the integral, so this is in 2 dimension, your d k is given by 2 pi k dk, right? That's in 2-dimensional case. So if you use these relationships, you can find this 2D density of state. If you do this integral for in terms of delta function integral, this is your density of state. This is very important. Remember, in ordinary materials, in 2 dimension, your density of state is a constant, right? So everybody should know, like in simple free electron theory. So if you take density of state of 3 dimension, goes like a square root of E, like a parabola kind of thing, right? So if you have a 2 dimension, so they are more like constants. So then you have sub-bands of this staircase like thing. If you have 1-dimensional case, that goes like 1 over square root of E. So then if you have a 0 dimension, that goes like a delta function, right? But in this graphene, that's completely different. Even 2 dimension, the density of state goes like linear relationship of E. So that means your density of state is going like this straight line. So you can see that that's why we have E O minus E this way. So density of state is given as 2 E over this value. So please remember the density of state for graphene is, we showed that one before, right? It goes like straight line near Fermi energy. So next I want to talk a little bit about electrical properties of graphene. So actually this is the most exciting thing. People measure the hole and longitudinal resistance of graphene. Basically what they have is, you have this graphene here. So then they pass current from here to here, the I. Then when they measure the voltage in the same direction, they get something called this rho XX. So then if you measure the voltage perpendicular to I, so then you get something called the Hall voltage. To do that one, you have to apply a magnetic field perpendicular to the sample. So then, since this is a field effect transistor, so they had this gate, so they could change the gate voltage and change the density of electrons in the system. So when they do that one at some like low temperature and high magnetic field, they found this something called this oscillations in the rho XX. Then they find these steps we call the quantum Hall steps for rho XY or sigma XY. So every time when you have this maximum, you get this when you get this 0 in your rho XX, you get a plateau here. So again, when you get 0 here, you get a plateau here. So this is standard quantum Hall effect. So, but interesting thing is, standard quantum Hall effect, you see these things in terms of E squared over H. So you see like 1, 2, 3 like that, E squared over H. But here they found this one to be this like 1/2, 3/2, 5/2, 7/2 like that. So this is actually a consequence of this pseudo spin in graphene. So instead of E squared over H, you get 4 because you have 2 coming from spin, ordinary spin, and 2 coming from the pseudo spin. Then also you have that sigma xy as some this E squared over H times n, but here you get n plus half. That's because of that pseudo spin. That's why you get this half 3/3. But if you do at higher temperature, so you see standard like 1 times 4 squared OH, 2, 3, 4 like that. So even room temperature people have observed that because you don't have that n plus half effect coming here. So also this graphene, you can change that here they do as a function of n. N is the charge density that you can easily change by changing the gate voltage. So that's what they did here. So you can change positive and negative because you can change the direction of your gate voltage to make it positive or negative. So this is a very exciting observation for graphene. So here is that one again. So also they found some other interesting properties like graphene can be ambipolar. That means they can be hole dominant or electron dominant. We call the p type or n type. So here you can see when you change your electron density, positive or negative, they find similar, very symmetric behavior in their resistance. So that's because in one side you get from when you positive bias means you are providing negative charges, that's the electron branch. If you are negative bias, you are providing positive charges, that's the hole branch. That's why you have this kind of behavior. So basically what you are doing is, this is your Dirac point, Fermi energy at the Dirac point. But when you do positive bias, that means you are moving your Fermi energy in the direction of this way into the conduction band. So if you apply negative bias, you are moving your Fermi energy into the valence band. So here are some of the other properties. You can see Hall effect. So you have this positive Hall effect and negative Hall effect, just like electron band and Hall branch. So same thing here. So you have with the gate voltage, you can see it's going positive and negative direction. So then graphene can be easily doped. Doping means, like I said before, so ideally you have your graphene Fermi energy here. So that means in equilibrium position, Fermi energy at the Dirac point. But if you dope it with the p-type dopant, that means you are taking out electrons from the graphene, or you are giving holes to the graphene. So then you will make your graphene the Fermi energy to move downward, or you can make Fermi energy to move upward if you dope it. We call n-type dopant or donor dopant. So you can see how they change here. So I'm going to stop here and continue from here next time. Thank you.